very, very basically. And this will relate to the other topic we're gonna talk about tonight. Basically, we're gonna talk about why Hess's law works in the first place. So basically, all reactions, it doesn't matter what the reaction is, as long as there are reactants going in and products coming out. You could break down the formation of all of those individual reactants and add all of those side reactions together. And basically it comes down to, it wouldn't matter how you produce those reactants or how they transform themselves into products. If at the very end, the net reaction out of, 4, 5, 6, maybe even dozens of reactions, if at the very end of all of those, the net reaction is, A plus B goes to make C, you can have as many steps in the middle as you want. It doesn't matter. As long as the net reaction, after you've summed all the reactants and all the products together, if the sum of that is your net reaction that you're looking for, you can take all the energies of those side reactions and sum all of those up, and they'll give you exactly the same energy that you would for the main reaction. So basically, you can break up a reaction to as many steps as you want, and the exact same amount of energy will either be expended by the system, or you'll have to put into the system to make it work, whether it's exothermic or endothermic. So we can calculate, and where this is really helpful actually, is there are certain reactions that are almost impossible to do. They're really, really difficult to do, but you could calculate how much energy would be involved in actually doing those reactions if you can figure out a series of reactions that will get you there when you sum them all together. And scientists have actually used this to figure out what sort of conditions they would need to do like a very, very difficult reaction. If it's like, extremely exothermic, they would know how to set up reaction conditions in a certain way. If it was extremely endothermic, they would know like to have the conditions be like very hot under like a lot of pressure or whatever. And you use Hess's law to determine that. So these are just the basic rules for dealing with Hess's law, for dealing with a process of different steps. We figure out first, what's the target reaction we're going for? It'll be A plus B makes C, if that's your overall process. Now you'll have a whole series of other processes, other reactions that may involve A, may involve B, may involve C. Some of them may be reactants, some of them may be products. There may be a lot of other reactants involved. But basically, if you add them all together and sum them, you get back to where you started. So what you want to do when you're doing these sort of reactions is first look for, where are my reactants? Where are they in the list of all the reactions you're looking for? Where are the products? Are they the right amounts? If they're not enough, you may have to multiply these reactions. If they're too much, you may have to divide these reactions. But anything you do to the reactions, you must also do to the energy. Because I think, as mentioned maybe in the last lesson, we can treat energy just like a reactant or a product. If it's an endothermic reaction, we have to put energy in to get it to work. So that's basically a reactant. Energy has to be added or the reaction won't work. If it's an exothermic reaction, then that's energy coming out. Whoa, coming out at you. That's a product. So it's being produced. Energy is being produced. So we can put that on the product side. And so if I multiply my reaction by 2, that means I'm going to make twice as much energy, or I'm going to require twice as much energy. Same thing as if I divide it by 2. I'm going to get half as much energy out, or I'm going to need to make half as much energy to go in. The other thing to remember is if an exothermic reaction, if I reverse it, becomes an endothermic reaction. In other words, if I take hydrogen and oxygen and blow them up and make water, that's an exothermic reaction going in this direction. If, on the other hand, I want to take water and convert it into hydrogen and oxygen, I need to add energy to that, usually like electrical energy of some kind. I need to add energy to it. Now it's an endothermic reaction going in the opposite direction. So then I have to switch the sign of the energy from negative to positive. And remember, an exothermic reaction means that the system is losing energy, so it's negative. If I have to add energy to the system to get it to work in an endothermic reaction, then it's positive. So all substances, when we add up all these reactions, everything other than what's in our original target reaction has to cancel out, or we haven't done it properly. So that's why I sort of like these questions. I think they're like sort of like doing a puzzle. And as long as you follow your math, make sure that you've done the alterations to the energy, just like you did with the overall equation. If everything sums up at the end, you're going to get the right answer. So this was the example we used last night. Just very briefly go through it. So this is our target reaction at the top. So let me do some drawing on here. Okay. So our target reaction is carbon monoxide and nitrogen monoxide, two fairly nasty molecules. You put them together, and this is what happens actually in your catalytic converter. If you remember, I mentioned that last night. Your catalytic converter in your car is actually a catalyst, which catalyzes this particular reaction to drop the level of CO and NO going into the atmosphere, because they're both rather nasty. So this is the target we want. We want to finish up with that particular reaction. And we don't know how much energy is going to be required. So engineers actually who would work on the catalytic converter would use Hess's law to figure out what reaction conditions would be best. Are we going to have to, should it be hotter? Should it be cooler? Should it be under pressure? Should we invent something that reduces the pressure? So they would use these two equations right here to figure that out. So first step, doing any of these sort of reactions, I want to look for where's my carbon monoxide, where's my nitrogen monoxide, look for the reactants. So then you look at equation A and you, oh, okay, there's my carbon monoxide. So I probably won't have to do anything to this one because it has carbon monoxide as a reactant, want that. It's got CO2 as a product, want that. And the numbers are right. The amounts are good. So I'm good to go with that one. Then we look for nitrogen monoxide. So nitrogen monoxide is on the product side of reaction B. So that's not going to work because I need it to be a reactant. So what I will do is switch this around so that the reaction goes in the other direction. So now it's a reactant, and my products are now going to be nitrogen and oxygen. When I do that, what do I have to do to the sign of the energy for this reaction? So I've reversed the reaction. What do I have to do to the energy associated with that reaction?
Reverse the sign?
Yeah, because it's an endothermic reaction when it makes nitrogen monoxide, but it's an exothermic reaction when I'm going in the other direction. So now I would say it's negative 180.6. What else do I have to do? There's a second problem with this reaction. It's not just the fact that the nitrogen monoxide is on the wrong side of the reaction. There's something else wrong with it too.
You have to divide it by 2.
Yeah, it makes too much. I don't want 2 moles. I just need 1. So I would divide it by 2. So basically when I do that, I use half a mole of nitrogen, half a mole of oxygen, and now only 1 mole of nitrogen monoxide. Now I have the right amount of NO that I was looking for. But now what do I have to do to the energy? Oh, go ahead.
You have to divide it by 2 too.
That's right. Because basically I'm making half the reactants that I was before, the products that I was before. And if you're only making half the products, and one of my products is energy, I'm only going to make half of that too. So then I would also multiply the energy by 1/2. I multiplied the whole reaction by 1/2. The energy involved with that reaction is part of it. So now I have to multiply that by 1/2 as well. And so when we do that, then we look at all the reactions and we add them together to see if that is going to work for us. So let's see if that works for us. So here's our solution. So just like we just did, we took equation B, we reversed it, flipped it around so that nitric oxide is now a reactant rather than a product, and we divided it by 2 or multiplied it by 1/2. So now the energy associated with that reaction is the reverse and 1/2 that it was originally. Now I add them together. And I think once you've got all of the products and reactants in your main equation, so this is our main equation, remember. This is what we're shooting for. Once you have all the reactants and products in the right amount, then you're ready to sort of go through and start checking to see if everything else cancels out. You cross your fingers and hope it does. So basically what you do is you add everything on this side of the reaction and everything on that side of the reaction. We add all the reactants together. We add all the products together. So there could be even like 5, 6, 7 reactions. If I'm really mean, I'll put it on a bonus question on the final with like 10 reactions or something. Maybe not 10. But yeah, so you want everything on the reactant side gets added together, everything on the product side. But before you do that, look and see if there's anything in common on both sides. Because if you have something that's a reactant and a product, anyone know what we call something like that? If you have a series of reactions and it's produced and then consumed, there's a particular chemical name for that. Anyone know what it is? It's not a product, it's not a reactant, it's both. And at the end, you have the same when you started. Go ahead.
We took it already in the lab. Is that the one?
What are you going to call it?
Oh,
Starts with an I. See if that helps.
indicator?
No, IN. T. I feel like
Intermediate.
Intermediate, that's right. It's an intermediate. And so it's important to the reaction because it wouldn't happen without it. But at the end of the reaction, you have exactly as much of the intermediate as when you started. And so basically, what we're looking for is intermediates in the reaction. So do we have any intermediates? Do we have anything that's both a reactant and a product here? Something that's in common between equation A and equation B.
The oxygen?
Yeah, the oxygen. So we have oxygen as a reactant in equation B, and we have oxygen as a product. Reaction as a reactant in A and a product in B. And it's the same amount. So what can we do with that?
Cancel out.
Yeah, we can cancel them. It's like it was never there. And we'll learn tonight why we can do that. Because basically, the same amount of energy went into producing that half a mole of oxygen as it took to consume that half a mole of oxygen. So energetically, it was like it was never there. Because basically, we added some energy and we took some energy away, and exactly the same amount. So we can just cross it out. So then we're left with carbon monoxide, nitrogen monoxide. Those are the only things left as reactants. And on the other side, we have carbon dioxide and half a mole of nitrogen. So we're done. It works. And so basically at this point, all we need to do is to make sure we didn't screw up our energies or our enthalpies. What's an enthalpy again? I can't remember what enthalpy is.
Heat or work?
It's what?
Heat?
It is heat, but a very specific kind.
Heat that does work?
Heat that doesn't do work. That's the
Oh, it
that's the
doesn't do
key. It's just heat without any work. So basically there's hardly any change in pressure or volume. So we call that enthalpy. So the first equation, we didn't do anything to that one. So as long as we remembered to write down its enthalpy correctly, we're fine. And the second one, remember, we divided it by 2 and then multiplied by 1/2. So you can always go back and check and make sure. Because when I do these problems, I like to write them, write down what I've done, and then check back and see what it looked like originally. That way I know whether, because if I've reversed it and divided it by 2, I want to make sure that I've done the same thing to the energy. So then we just add them together and see that the overall reaction of our new reaction would be a sum of both of those. Okay? And we'll be doing a number of those, believe me. Here's another another good one to do. So basically this is burning a fuel. So here we have a fuel, that's ethanol. And so we're burning ethanol in the presence of oxygen. And when we burn a hydrocarbon in the presence of oxygen, we're going to get good old CO2 and water are going to be our two products. So we need to use these two equations down here, A and B, to figure out how to get there. So you can see that we've got a whole lot of different things to look at. So we want to look for ethanol. Ethanol is, let me get a different color. Ethanol is here as a product in A. We want to look for oxygen. Oxygen is also a product in A, and I don't see it anywhere else. Now, carbon dioxide. Where am I going to find carbon dioxide? Oh, there's also oxygen here. Duh. So there's oxygen in both reactions. So that might be tricky. So where am I going to find carbon dioxide? That's my first product. Where do we find it in equation A or B?
In the reactants for B?
That's right. It's right over here. And water is in both. So when you have a situation like that, we've got oxygen in both and we've got water in both. So we can't really use those to multiply and divide. So what we'll do is use the ethanol and the CO2 as a guide, because there's only one source of both of those. Okay, so we'll start with doing that. Let's keep going. So how do we come up with a solution for this one? So this is the overall reaction we're looking for. Just let me go. So we want to, I should have done this a little bit better. So we want to combine A and B. So it looks like we're probably going to have to, what are we probably going to have to do here? Actually, let's make some predictions. What are we going to have to do to A in order to make it fit with our overall reaction?
Flip it and divide it by.
Look, most likely, right? Looks like we're going to have to flip this one so it goes this way, and we're probably going to have to divide it by 2 because we have 2 moles of ethanol. We only want 1. Now, what about the CO2? For equation B, what are we going to have to do to that?
The same.
Excuse me?
We keep it the same.
We're going to keep it the same? Exactly the same?
You have to flip it.
Yeah, we're going to flip that one too because CO2 is in the wrong place. It's a reactant. We want it as a product. So we're going to have to flip that one. And what do you think what else do you think we're going to have to do? Probably that's it, right? Because it's the right amount of CO2. And then we just sort of hope for the best. So the energy, so this one is going to become negative. This one's also going to become negative and multiplied by 1/2. So let's see how all that works out. Yeah, so we divide reaction A by 2, and we reversed it, and we reversed reaction B. So then add everything up. So let's start adding them. So we've got we're looking for things that are in common on both sides. So this will be important because the first couple of examples we've looked at, if we have something in common on both sides, we can just cross it off. But in this instance, we're going to have things in common on both sides, but not the same amount. So that'll teach us something important, hopefully. So what can we get rid of? What do we have on both sides that we can get rid of? So we're looking here, we're looking at these two. What things are in common on both sides of there's reactants and products?
The C2H4O.
Yeah. That's here. And it's here. But this time it's exactly the same amount, so we can cross that out. What else do we have in common? That's about it, right? That's the only thing that's in common on both sides. Now, we just add everything together. So I have 1 mole of ethanol. There's my 1 mole of ethanol. I have 1/2 a mole of oxygen plus 2.5 moles of oxygen. And I just add them together. So now I have 3. And on the other side, I've got my carbon dioxide. I got 1 mole of water from this reaction. I got 2 moles of water from the second reaction. So that's 3 moles of water. And that's what I was looking for. 1, 3, 2, 3. 1, 1, 3, 2, 3. So that's what I'm looking for. And then whatever I did to the reactions, I do the same thing to the energies and sum them. And I see overall I've got an exothermic reaction, which you should expect you should have, because after all, you are burning something. It's a combustion reaction. It should be exothermic. If you're doing these sort of reactions and you notice that it's like, anything plus oxygen and it becomes endothermic, you probably switched something wrong. It should be an exothermic reaction. So any questions how we do that?
Yes, on the exam, do you want us to have like the liquid and the gas label?
Sorry, I couldn't quite hear you.
On the exam, do you want the liquid and the gas label?
Yes, that's going to be very, very important. In fact, we may have, I need to check and see if I have any examples. But yeah, it's super important to have the stages. Because actually the experiment we're going to do tomorrow, the state of matter is going to be extremely important. Because you'll notice here, water is a liquid rather than a gas. And generally when you burn something, you don't get water as a liquid. You usually get water as a gas, right? So one of the reactions you might get is a reaction like this. You might get H2O liquid goes to H2O gas with a delta H associated with it. Now, would that be an endothermic reaction or an exothermic reaction? Taking a liquid to a gas. So what do you think? Like H2O liquid go to the H2O gas. Is my enthalpy going to be positive or is it going to be negative? Yeah, nobody wants to guess?
It'll be negative.
Why is that? Oh, negative, what does that mean? Exothermic or endothermic?
Exothermic.
Exo, so think energy will be released when we convert a liquid to a gas. What happens on your stove? Is energy released when you boil water, or do you have to put energy in to boil water?
You have to put more energy in.
Got to put energy in, right? Yeah, I mean, you got an electric range or you got a gas stove or something. You got to put energy into, you got to put thermal energy into that to make that happen. So that would be positive. That would be an endothermic reaction. So you would sometimes on some of these, you will find that one of the reactions is just a physical reaction of turning something from a liquid to a gas. So it's really important for the states of matter. And tomorrow we're going to be doing a reaction where we're going to be taking sodium hydroxide solid, and one of the reactions is going to be sodium hydroxide solid to sodium hydroxide aqueous. That's going to be one of the reactions, and it has the heat associated with it. And it's important that we notice or calculate or leave this into our calculations that is a reaction by itself that requires energy or releases energy. You'll see tomorrow. So yeah, the state of matter is really important for these because there's energy involved with each state, and it's different depending on what it is. That's a great question. All right, so now we're sort of getting to why Hess's law actually works. And so what we're dealing with here is what we call a standard enthalpy of formation. And the standard enthalpy of formation for any molecule is basically how much heat does it take or is released when you make a molecule from its constituent parts. So how much does it take for us to make 1 mole of CO2 from a mole of solid carbon and a mole of oxygen gas? And so all of the constituent elements should be in what we call their standard low energy state. In other words, at 1 atmosphere of pressure and 25 degrees C, not 0 degrees C, because we're not dealing with gases. But basically, what's the most stable form of all these elements at 1 atmosphere of pressure and 25 degrees? So for carbon, well, it's simple. It's graphite. Solid graphite is the most stable form of pure carbon. The most stable form of pure oxygen at that stage is O2. Not O, not O3, O2. That's the most stable form of oxygen. And then for an element, we will see that the standard enthalpy of formation of an element is going to be 0, because we have to basically start this, start these numbers somewhere. And so basically what we do is we give each of the elements in its most stable form at that particular temperature and pressure. The standard formation of the element by itself will be 0. And so basically we can put this together and say that it's going to release exactly 393.5 kilojoules to form CO2 from solid carbon and oxygen. And we don't have to take into consideration how much energy it took to make the carbon and make the oxygen, because they're elements in their most stable form, okay? And we'll get into why that's important. So these are the various heats of formation for common things. And so you can see anytime we have an element in its most stable conformation at room temperature, it's 0. So bromine as a liquid is 0. But bromine as a gas, we need to put in some energy to get it to be a gas. We need to put in that much per mole. Same with chlorine. Chlorine is a gas at room temperature. But if we want to split those two chlorine atoms into separate atoms from the molecule, we need to put in energy. And what's some of the, sulfur. The weird thing, one of the weird things, sulfur is weird for a lot of reasons, but its most stable form is S8. Not just S or S2, it's S8. So we have to take that into consideration if we're making something out of sulfur. Nitrogen, you can see nitrogen is 0. Oxygen is 0. If we want to make ozone, we want to add another oxygen. That takes energy to do that. But notice most of the other common compounds are basically all exothermic reactions. And that kind of makes sense, because if they didn't release energy and become more stable, we probably wouldn't see so much of them. Like, especially ionic compounds. Ionic compounds are much more stable than their atoms. And we learned this, remember? Because we took sodium atoms, which really don't like to be atoms. They want to be ions. And we took chlorine, which really doesn't want to be chlorine, wants to be chloride ion. It's much more stable. So if you take sodium and chlorine and put them together, that's going to be an exothermic reaction. That's going to release energy because it's much more stable than it was before. Any questions about about what these numbers mean? You sort of wrap your brain around with this standard enthalpy for formation. Like SO2 here, basically take 1 mole, to make 1 mole of sodium, 1 mole of SO2, you take 1 mole of O2 and an 1/8 mole of S8, and you put those together, and that releases that much energy. So all of these per mole are for per mole of product. So 1 mole of calcium oxide, 1 mole of carbon dioxide. And any amount of the original components to get you to that 1 mole. So we use standard formation just like we would use the enthalpy for anything else. So we write a balanced equation, and then we can figure out how much energy is involved in that balanced equation just by looking up how much energy it took to form these particular compounds, okay? So you write all the elements as reactants. So for the first one, we would have just silver and chlorine. But for the second one, we would have calcium, carbon. So calcium is a solid, carbon is a solid, and O2 as a gas would be our 3 components. And then for hydrogen cyanide, it would just be H2, C, and N2. So each of the standard enthalpy of all these things to form all these things would be 0, okay? So let's see how we would just write those out. Oops, done the other way. So the first one, we always have to make sure that we're using the most stable form. So instead of chlorine, instead of chloride, remember chloride isn't the most, that's not what we see at room temperature. We see chlorine gas. So we need a 1/2 mole of that. And that would be our, that would be our formation. So the second one, as I mentioned, solid calcium, solid carbon in the form of graphite, and 1.5 moles of oxygen. Add all those together, and you get CaCO3, calcium carbonate. And then the last one, to make hydrogen cyanide, you only need 1 atom of hydrogen, so half a molecule of hydrogen, 1/2 molecule of nitrogen, because you only need 1 atom, and a mole of graphite. So as far as where would we put the heat? Would we put the heat on the product side or the reactant side for these 3? Where would you put it for the first one? If I was to put this as a product or a reactant, where would I put it?
Reactant?
Now remember, it's losing 127
Okay.
kilojoules. So it's releasing 127 kilojoules, just like a product. Yeah, so we would put it over here, plus 127 kilojoules. Because basically what we get from this reaction, we get both solid silver chloride and we get 127 kilojoules of energy released. So what about the second one? Is this a product or a reactant?
Product.
That's a product too. Yeah, because it's, and actually you can see that releases a lot of energy. This is very stable. Basically, when you react anything with oxygen, it becomes much more stable. So yes, you release a lot of energy when you react things with oxygen. And the third one, this one here, we're putting energy in or taking it out?
And a reactant.
Yeah, we're putting it in.
Mhm.
That's an endothermic reaction. So we would be adding 135 kilojoules as a reactant. That's right. Okay. So we're looking at basically, there's a couple of different reactions that we're looking for. So we start with our elements. So we have our elements up here at the top. And we have our products down here at the bottom. And generally our products are going to be more, usually our products are more stable than the products. So generally, these are the reactants going in, these are the products coming out. And when the reactants decompose. So this is a reaction we're talking about. So I'm starting with a molecular reactant. Let's say I'm starting with CH4 and O2. So I've got methane and I've got oxygen, and I'm reacting them. It's a combustion reaction. We think about what happens when we get up here. We're basically pulling all the bonds apart and converting it to just carbon and hydrogen and oxygen. Basically, we're just pulling them apart. That's called a decomposition reaction, right? We're actually pulling these things apart. And when you do that, when you break bonds, that takes energy. You need to put energy in to break bonds. And that's what we're doing. We're breaking those carbon-hydrogen bonds in the methane. We're breaking those apart and forming elements. So that takes energy to do. But then we're taking these things and then we're forming bonds. And it may seem strange at first. I remember I thought it was strange at first. You actually release energy when you make bonds. So actually when you're burning wood, it's not the breaking of the carbon hydrogen, carbon oxygen bonds that's releasing the heat that makes you warm. It's the formation of the CO2 and H2O bonds. It's the formation of those bonds with oxygen. So you're forming new bonds, whereas carbon used to be bonded to hydrogen. Now the carbon is going to be bonded to oxygen, and the hydrogen is going to be bonded to oxygen too. And like I said, when oxygen reacts with something, it's generally forms something more stable than it was before. And so our products here are now going to be more stable. So how do we figure out what's going to be our heat for the overall reaction? And what we have to do is we have to think about all the bonds that we broke on this side. So we broke these bonds on this side, but then we formed bonds on this side. To notice our energy went up. We had to add energy to break the bonds. And then we got energy back when we formed the bonds. So basically we can figure out the energy of any reaction if we knew how much energy it took to form the reactants and how much energy it took to form the products. And we could just subtract the difference. Because basically this is what we have here. The difference for the reaction over here, that difference is how much energy it took to break these and how much energy we got back forming these. So if we know the standard enthalpy of formation of all the reactants and all the products, we can just add them together. And that is why Hess's law works, because basically it's the same thing. We're doing exactly the same thing. We're just taking our molecular products and we got a whole series of reactions to make them. We got our products and we got a whole series of reactions to make those too. And if we add them together, we'll come out with the same reaction. But the thing to remember here, this is really important, that we take the heat of formation of the products and we subtract the heat of formation of the reactants. And the way to remember this is, remember, we break reactants. We pull reactants apart. And so that's going to be opposite of forming them, right? So if we know what delta H formation is, delta H breaking them is going to be exactly the opposite. And we want to know how much energy it takes to form the products. We're forming products, that makes sense. So we're going to want to calculate that, but then we're going to subtract from that however much energy it took to form the products. So is that clear to everybody, how that works? We're breaking on one side and we're forming on the other.
So that's meaning in the breaking and in forming, it should be the same, the change.
No,
Mhm.
one is the opposite of the other. So the information we're going to get when we look up the heat of formation, so we're basically just going to have a big sheet of the heat of formation of all these different things. So if we want to figure out the heat of formation of any reaction, basically delta H of any reaction, all we need to do is figure out how much energy it takes to form reactants. So we're going to find out how much energy it takes to form reactants. That's what delta HF means. And we're going to find out how much energy it takes to form products. Those will be our delta H for the products. These are going to be for the reactants. But when you think about it, we're not forming reactants, we're destroying them. We're pulling them apart. So I can't add these two together because I'm doing the opposite of formation on this side. I'm literally doing the opposite of forming. I am breaking them. So I need to subtract this value, whatever it is, because I'm doing the opposite. And you remember, whenever we do the opposite of a reaction, we flip the sign. So that's why down at the bottom here,
But the value by itself, it's gonna be same. It's just like different sign.
I'm
Correct?
sorry?
I
The
said,
value, the absolute value will be the same. So we take all we add all the delta H formation for the reactants. We add them all together and then we flip the sign. So right here.
Okay.
So the sigma, remember the sigma means sum. So we sum all of the heat of formation of all the reactants and we flip the sign. Whatever it is, it might actually be negative and we'll flip it to be positive. And then we take all of the energy it takes to form all of our products and we add those together. So we sum all of those. Okay, and we'll do some examples to drive this home. But basically, it's this relationship that shows why Hess's law works. Because we're doing the same thing here. We're just figuring out, instead of any particular reaction, we're figuring out very specific reactions of forming the reactants and forming the products from their original elements. So let's sort of look at an example. Maybe it would help. Okay. So let's speak of the devil. So we're going to make nitric acid, because who would want to make nitric acid? So the first step in producing nitric acid is oxidizing ammonia. So here we have ammonia. We probably should be fairly familiar with ammonia at this point. So here's our ammonia, and we're oxidizing it, so pretty much know what that means. And then the product of those two is nitrogen monoxide and water. And then we just oxidize it, then we react the nitric oxide with water and come out with nitric acid. So what we can do here, if we can calculate how much energy it took to form the ammonia and how much energy it took to form the water, added those together, and then subtracted it from the amount of energy it took to make NO and the amount of energy it took to make water. We add those two together and we subtract the formation of these two. So anyone know what's going to be our heat of formation for the oxygen?
0.
0. Someone was paying attention. Excellent. Yes, 0. So this will be 0. So that'll be pretty easy. Then basically all we need to do is just look up ammonia, NO, and water. Just need to look up those 3. And the other thing you have to do is, because remember that the heat of formation is per mole. Anytime you see a delta and a capital H, assume that means per mole. So we're going to have to multiply this one by 6, this one by 4, and that one by 4, because we need 4 moles of ammonia, and we get 4 moles of NO, and we get 6 moles of water. Oop. All right, so let's go ahead and do this one. So we just use the values that we had before. I'm not going to go back and show you. We can, if you get them on a test, I'll give them to you. And we just apply that equation, like I said. So here are our products. NO and water are our 2 products. And ammonia and oxygen are our 2 reactants. And we can ignore the oxygen, as it was pointed out. There's no energy into forming that. Right, so here's our values. So ammonia, minus 45.9. So that's an exothermic reaction. The formation of nitric oxide is endothermic. It takes 90.3. Oxygen is going to be 0. And since water is hydrogen reacted with oxygen, we know that's going to be exothermic, because everything reacting with oxygen is exothermic. And so, because it's going to be more stable. So we just put those, get those numbers, put them together. Oops. How come I'm not getting the hell? Oh, for some reason, it's not showing you the answer. Oh, damn it. Anyway, I don't know why, but here, let me see if I can pull it up for you. There we go. So yeah, like I pointed out, 4 times, because we're dealing with per mole. These are all per mole. So 4 times the heat of formation of nitric monoxide, 6 times for water, and then we subtract for that 4 times for ammonia, because there's 4 moles of it, and then 5 for oxygen, which is going to be 0. Just sum them all up, add them all together, and you can see the end of it, the final reaction is going to be exothermic as well. So what we're doing here is basically we're still doing Hess's law, only basically now we know what all the reactions are. We're dealing with just the formation reactions. That's it. Just the formation reactions from the elements from where they were, from whence they came. But it's the same idea. We're just summing them together. Oh, damn. Okay. All right, so here's a question. When you get, so pretty much we know what we have to do when we make water boil. We just talked about it a second ago. We have to add energy to it. Second part of the question, I asked this when I was volunteering in the high schools, and nobody was able to figure it out. You get into the water, you feel cold, even if the room is warm. How come?
Because the inside our body temperature.
What about the inside of your body temperature?
Our body has to adjust to room temperature.
Nope. No, I'm saying even if the room is warm, you're going to feel cool for a second, and then you're going to warm up again. So why do you think what's going on like on a molecular level?
The
What's
water's-
happening on your skin that would make you feel cool?
The water? Still on
What
your
about
skin?
the water?
It's evaporating.
It is evaporating. What kind of reaction is that? That is this reaction. What kind of reaction is that?
Endothermic
It is endothermic. Where's the energy coming from?
from your body.
That's right. You're doing it. So you are putting in the energy. You're putting in the delta H here to convert that water that's on your skin into a gas. And when it evaporates, that's why when it evaporates, you feel cool, because it's an endothermic reaction that removes energy from the system. And that energy it's removing is from your skin. And so you feel cooler. Of course, as soon as all the liquid water is off you, then, like, you know, especially if you're in someplace really, really humid, that water may not evaporate off of you and you're not going to feel any cooler. But if the humidity is, you know, relatively low, yeah, you're going to feel cool. So why is that important? It takes energy to vaporize. So, quick states of matter. We were asking whether states of matter are important. You're going to see it's extremely important, especially when we're dealing with energy. So, I think we've sort of been learning for a little while now that the only difference between the states of matter is how fast their molecules are moving. That's pretty much it. So if it's a solid, molecules aren't really moving much. They're interacting a lot with each other. You move to a liquid, they're moving more. Now they're starting to move around. So you see in a solid, they're all sort of together. In a liquid, they're more disordered. They're still interacting with each other, but much more disordered. They're free to move relative to each other, so they can flow, whereas a solid does not flow. Then you add even more heat, you get to gas, where the molecules are moving very, very quickly. It's completely disordered now. There's no interaction, or very, very little interaction between the molecules. They have complete freedom of motion, and they're far apart from each other. So the phase depends on how much energy each molecule has. So the more energy we add, the more disordered it becomes, the more disordered the phase becomes as well. So, and that is going to have some profound effects on how we calculate energies. These are the different phase changes. You're probably familiar with a lot of them. Some of them you may not be, especially dealing with gases and solids. But everyone pretty much knows that when you take a solid and you turn it into a liquid, we call that melting. Well, duh, yeah, kind of figured that. Liquid back to a solid, well, that's freezing. Okay, sure. And then a gas, when we turn a liquid into a gas, we vaporize it. Well, sure. Some of these other ones may not be as familiar, but I think we may be familiar with condensation. Like first thing in the morning, when there's dew on everything, there may be dew on the hood of your car or on the car window, and you got to wipe it off. Or that's just from water vapor. When it got cold over the night, the water vapor then condensed into a liquid on things. So we call that condensation. Then some of these other ones are a little weird, like gas going directly to a solid. We call that deposition. You see this with iodine. Iodine does this. Iodine doesn't really have a liquid phase. It goes directly from a gas to a solid. So when we cool it down, you can like warm up iodine crystals and they'll turn into a gas. That's called sublimation. We say it sublimes from a solid into a gas. And then you can cool down that gas. It's kind of fun to do because it makes really pretty crystals. You put like, you know, a beaker or something with the ice water in it. And that gas then will deposit on the beaker or the flask. And you get these really pretty purple crystals. So we call that deposition. So these are the different phase changes we'll be dealing with. And there's energies involved with all of those. So note how different energies react differently when we add heat to them. So we call this a phase change diagram. And what's it a diagram of? It's the amount of heat on the bottom as we add heat to something. What is the temperature of that thing? And in this particular instance, we're looking at water. So what happens to the temperature of water when we add heat to it? Well, it goes up, duh. Not always. So watch what happens here. So here's our temperature as we go up. So we're adding heat to it. So we start with ice. So we're at like minus 25. So we're gonna have ice, that makes sense. And we add heat and we add heat and the temperature goes up and up and up until it transitions. And then notice, we're adding more heat, but the temperature doesn't change. And then we add more heat and then, oh, temperature starts going up again till we get to another plateau. And it doesn't change again for a really long time until we get to another change. And then we start adding more heat and the temperature goes up again. But look how it is not continuous. This is not a straight line all the way up. It is discontinuous. So notice, when is it discontinuous? Can anyone point out at what points is this graph discontinuous?
It's when it changes from like ice to melt, then when it changed from water to vaporization.
Right, whenever there's a phase change,
Yeah.
whenever there's a phase change, the temperature will remain the same until all of the until the phase change is complete. So this is why when you boil water on the stove, it stays at 100 degrees. Whoops. It stays at 100 degrees. It doesn't get higher. And you just keep adding heat and keep adding heat and keep adding heat. It stays at 100 degrees. And it's going to stay there until all of that water is gone. And then all you've got left is gas. Then you can just increase the temperature of the gas all you like. Increase the gas temperature pretty much infinitely. But as long as it's a liquid converting to a gas, as long as it's changing from one state to another, the temperature remains constant. Notice while it's all liquid, for the temperatures between 0 and 100, you got no ice and very little gas. And so it's pretty much all liquid at that point. So the more heat you add in, just increases the temperature of the liquid until you get to 100, and then it's all converting, all that energy goes into converting liquid to gas. And the same thing is true with freezing. The ice will just keep increasing in temperature until you get to 0. And then at that point, all of the energy going into that ice and water goes into melting the ice, not changing the temperature of the water. That's why my ice water here will stay pretty much exactly the same temperature all the way through until all the ice is melted. then it'll start to increase in temperature. And so we can calculate exactly how much energy it takes at each one of those stages. And one thing to take away from this, notice how much more energy it takes to vaporize something than to melt it. I mean, it's not terribly surprising that that would be true. But look at the distance from B to C here. It's very, very small. But the distance from D to E is very, very large. It takes a lot more energy to have so much energy added to the molecules that they can move completely randomly and at great speed. Whereas if we took molecules that were moving very slowly and then allowed them to melt and move a little bit more, that takes some energy, but not nearly as much as it takes to sort of basically liberate them completely from each other. So what we're going to do is look at all these different stages and see how we can calculate these different changes. There's a couple of different things going on. So from a solid to a liquid, we're melting. From liquid to a gas, we're vaporizing. Now, are any of these exothermic reactions? So remember, we're looking at heat is on the x-axis and temperature is on the y-axis. So would we consider melting or vaporization exothermic or endothermic? Are we putting energy in or are we getting energy back? Oh, somebody guess, come on.
Endothermic?
What is it?
Endothermic?
Endothermic. Yes, definitely endothermic. Because we have to add energy for these two things to happen. Melting and vaporization just aren't going to happen on their own without energy going in. That's right. So notice that these things are endothermic. So when on those curves does the temperature increase? At what point do they increase? When you go back, what point do we see increasing temperatures? Is it when we have one phase or we have a mixture of phases?
When we have one.
Exactly. When we have just one. When there's just one phase, or mainly one phase, all the energy goes into increasing the temperature of that phase. Now, when does the temperature remain constant? Let's go back. When does the temperature stay the same? It's just a straight line across.
When it in vaporization,
During vaporization, and when else?
liquid water.
No, when it's the liquid, it's increasing in temperature. Where's the other point where its temperature staying the same?
From B to C.
From B to C, right. So what's similar between the segment D to E and B to C? What's similar between those two?
When they're in between phase changes.
They're in between phase changes, that's true, and it's a mixture. So you have a mixture of phases. You have ice and liquid when it's melting, and you have liquid and gas when it's vaporizing. And so when you have two phases together, basically all the energy is going into increasing the energy of one phase to to match the second one. So if I have solid and liquid, all the energy goes into the solid becoming a liquid. If I have a liquid and a gas, all the energy goes into turning the liquid into a gas. Once everything's a gas, hey man, it's a gas. Once everything is a gas, then the energy goes into increasing the temperature. And then all the molecules start moving much more quickly, and everything becomes a gas. So we can calculate these things, gained or released during phase changes. And so we call them fusion. That's basically the heat that's involved in either melting something or freezing something. We just call it the heat of fusion. It's going to be positive from one direction, and it's going to be negative in the other. Which direction do you think it's going to be positive? When do we see like positive fusion energy? Melting or freezing? When would that delta H be positive? Oops.
Endothermic,
For which one?
when it's endothermic.
Right, when it's an exactly. So this will be delta H fusion will be positive when it's endothermic and negative when it's exothermic. So which one of these is endothermic and which one is exothermic? Melting or freezing? Which one's endothermic, which one's exothermic?
Melting endothermic?
It is. Melting is endothermic. We need to put energy in to melt something. It's not going to just melt by itself. We need to add energy to it in order to get it to melt. So delta H fusion for melting is going to be positive because that's energy we need to put in to make that happen. It may seem weird to think about, but freezing is actually an exothermic process. It's like, yes, because we're taking something that's liquid and we're removing energy from it so it becomes a solid. So it's actually releasing energy when it does that. So that is actually an exothermic process. And so the heat of fusion will be exactly the opposite. Basically, we're going in one direction when we're freezing and we're going in the other direction when we're melting. So heat of fusion is positive, melting, negative when it's freezing. And we call that the latent heat of fusion. And this comes with that delta H with the little FUS, no fuss. So the energy required to melt something, or when a substance freezes, it's exothermic, and it's the amount of energy given off. And this is how we calculate it. Very simple formula. So again, Q, because it's heat we're dealing with, it's Q again, our good old friend Q. And so it's just mass times the heat of fusion. Can't get much more simple than that, right? So basically the heat of fusion is going to be the number of joules per gram. That's going to be our heat of fusion, okay? And so our heat of fusion for water is 334 joules per gram. So we have to add 334 joules of energy for every gram of ice to turn it into a liquid. And for every gram of liquid we turn back into a solid, we release 334 joules of energy, okay? Which is weird because we have to add so much energy to a refrigerator to get it to do this. You'd think it'd be the other way around, but you know, that's how it works. So make a note that the heat of fusion is 334. So our other phase change is going to be boiling. Or vaporization. So either we're boiling something or we're condensing it. And that happens at 100. Our other reaction takes place at 0 and only at 0. So remember, at 0 degrees, it plateaued and all it's doing at that point is melting. So that's why there's no temperature in our heat of fusion. Same with vaporization. We have a latent heat of vaporization. So it's going to be positive when we're boiling something, and then negative when it condenses back. Same equation. And look at the difference in energy. So it took like 330 to melt something, but it takes almost 8 times that much in order to boil it. So the other thing to take away from this is this happens at one temperature. And so when we're doing our calculations, like how much heat does it take to go from ice cube to a gas, we have to remember that our heat of vaporization, when we get to 100, just heat of vaporization. That's all that's happening. At 0, heat of fusion. That's all that's happening. But what's happening during the other points where we have a pure state, we have a pure liquid or a pure solid? God damn it. Here we go. So at those other stages, I'm going to skip this because it's fairly easy to do. Oh, so I didn't have that slide. I'll just show you it later. At those other stages, basically what happens is we're looking at the how much energy does it take to increase the temperature? That is our old friend, the heat capacity. So the heat capacity tells us for a liquid, for water as a liquid, it's 4.184 joules per gram per degree. That's for the liquid. For the solid, it's a different amount. For the solid, it's a different heat of capacity. And for the gas, it's a different heat of capacity. It's just for the liquid, because that's what we've been dealing with so far, 4.184. But I'll show you some of those calculations next class. Any questions what we went over tonight? Or on anything?
So just I want to make sure when I put energy, I mean when I need energy, the charge is positive, correct?
Yes, when you're putting energy into a reaction, that's
It's
positive, and we call that endothermic.
Mhm.
When energy is released from the reaction and given to you, that's negative, because the system, the reaction is losing energy. So we say that's negative.
So when it's in product, negative. And
Right. When it's a
reaction,
product, it's
positive.
released.
Okay.
Yeah, it's given off as a product. It's being taken in when it's a reactant. Yeah. Okay, so grab a snack and have fun with these calculations. You're going to be doing some more of these Hess's law. I guess not everyone finds them as fun as I do. What can I say? I'm a nerd. Anyway, so if there isn't anything else, I will bid you good night, and I will see you for lab tomorrow afternoon. We're actually going to put some of these principles to practice. Okay? And I'll try and make myself not look so damn red, man. I look like I've been out in the sun for like a month or something. All right, we'll see you later.
Thank you, Professor.
All right, thank you. We'll talk to you soon. Bye-bye.